A very good morning to all of you. Thank you for joining us. I'm Vasudha Sridharan, and on behalf of Cumulus Networks, I'd like to welcome you all to the next episode of Demystifying Networking webinar series. We will be discussing microservices network architecture today. Presenting today will be our very own webinar host, Dinesh Dutt. This webinar will be about 16 minutes, and we will have a short demo in the presentation. We'll answer questions from the participants during the course of the presentation. For those of you interested, you have the opportunity to ask questions during the webinar by using a window marked questions. Simply type in your question and click send through the chat window. You can also tweet your questions to us. Our Twitter handle is @CumulusNetworks. And with that, I'd like to turn this over to Dinesh.
Good morning, good evening, wherever you are. Thank you for taking the time to come attend this presentation. We hope to make it an interactive session, so please feel free to ask questions as you have them. I'll try and address them at appropriate breaks. I'll try and demonstrate whatever it is that I'm doing as we talk and we cover a particular concept. So there will be no demo at the very end, but in between as well. So there will be a small pause between as I switch screens so that I can start sharing my screen of the terminal while we are doing this. With that, let's get started. Today we'll be talking about Microservices Network Architecture 101. Last month we presented Kubernetes and how you can do Kubernetes networking. And one of the things that I got as feedback from a lot of people was that was extremely deep end and that they would really like to understand some basic principles. Some of the people ask questions like, I don't even know how containers on the same host talk to each other. I also don't know, can a container on a host talk to somebody that's also running on the same host but is not a container? What about containers that run across multiple hosts? How do they talk to each other? So there were some very elementary questions that were asked, and we said, okay, using that as feedback, let's take some time and actually talk about the basic concepts. So I'm assuming in here that you know nothing except you heard containers, you know Docker, you've heard about it, nothing more than that, and I presume you know basic networking, what's bridging, what's routing, and simple things like that. So I hope to cover the initial part of this presentation is going to be, this presentation is going to be fairly straightforward and simple, but there are some interesting aspects of a networking guy looking at container networking, which was primarily designed by people who are running on the compute side of things. So even people who think they know the basics of container networking, I hope to show you some interesting aspects of what can be achieved. The second part of what's going on is that as part of all of this, there is another aspect to talking about container networking. If you are a networking admin, you might ask, why do I need to know about containers networking? I'm a networking guy. I run routers and switches. I manage routers and switches. What interest is container networking to me? One of the things you'll realize, I hope, as coming out of the session is why that matters. Container networking is the next evolution of application architecture, and as networking serves the needs of applications that run on top of it, understanding what containers do is interesting. More importantly, networking is now becoming the focus of many aspects. It's no longer restricted to what was done on the networks, which are switches and routers, and nothing is done on the host itself. So with those aspects, you will see how some of these things change as we move forward and understand about container networking. If I have three key takeaways that happen from here, I would say that the three takeaways are essentially microservices are the latest step in the evolution of application architecture. What they serve is essentially make application development faster, scalable, and adaptable. Container networking has two primary modes. And using well-known techniques, multi-host networking, container networking can actually be made much more easier than has been traditionally seen. And we'll look at each of these three pieces. But I hope if you have three takeaways, these would be your three key takeaways. So let's look at the evolution of microservices. I hope to also do some level set in terms of terminology, in terms of understanding what are the different pieces, what is IPVlan, what is MacVlan, what is Flannel, what is some of these other terminologies that exist and how they tie in with concepts that you already understand, such as VXLAN, such as routing, such as bridging. I also want to talk level set a little bit about what microservices is without going too far into each one of these concepts. So many moons ago, in a galaxy not so far away, monolithic apps were essentially the du jour. You had mainframes, the application ran on the mainframe, a person had a terminal server and they connected to it, they had badge jobs, everything was just the mainframe. The application was a monolith, as was the computer on which it ran. Then came the evolution, the next evolution, PCs started becoming more and more popular. As PCs became more and more popular, the client-server architecture started to happen, where the monolithic application was broken up into a client and a monolithic server. The monolithic server and the clients were connected via a LAN, typically, because this is how it all began. But then what happened, the internet took off, and now you had the same server running, but you had lots of clients connecting. And in order to scale the application, a single monolithic server alone did not make sense anymore. So what people did is they took the monolithic server and broke it up into 3 pieces. As an example, essentially tiered applications became the du jour. You had, for example, a web front end, an application, and a database tier. Then came server virtualization. And what that meant is, even though I had broken my application into 3 separate pieces, it was still hard for me to scale as the number of users kept growing and growing. And so I said, instead of trying to grow so many, I couldn't multi-thread my applications because multi-threading and rewriting applications was pretty hard. So server virtualization came along, and what it did is it just allowed you to run multiple instances without requiring multiple physical servers. This allowed you to scale your applications because each VM used 1 core, for example, but you could run multiple of them. So server virtualization allowed you to start scaling your network horizontally. You had multiple instances of web front end, multiple instances of application tier, multiple instances of database tier, etc. And each of these tiers spoke to each other through a load balancer, which allowed you to somehow anycast and provide these services without knowing where each individual server resided. And this allowed you to scale as the number of clients started scaling. And then came containers. When containers came along, the world itself has changed again. No longer did you have a common way of accessing the applications. You were accessing applications now through mobile. You were accessing the same application through mobile, but through the browser on the mobile instead of an app on the mobile. You had tablets. All of these started changing the form factor of how people used applications, viewed applications, and that started changing again how these applications evolved. One of the things that happened, for example, is, hey, I have an application, and because I had a web front end, the web front end was based on a particular framework. Well, now with mobile, with tablets, and various shapes of desktops, things could no longer be static anymore. You needed new frameworks. You needed new technologies to be able to deal with all of that. And instead of continuously trying to take each monolithic piece and trying to evolve that, they said, why don't we break it up even more further and make it such that we can evolve each individual piece as the technology changes, have well-defined interfaces between these different pieces, so each particular piece provided one little service and everybody communicated with each other through well-understood interfaces. In many ways, containers is a hark back to the Linux model, where in Linux, or Unix more precisely, there were things that were very simple. They did one thing and they did it well. And then you took all of these different things and you piped them together, you connected them together to construct a more complex piece that did more interesting things than just what this little piece did. But given that this little piece did one thing and it did very well, it could be used multiple times in multiple situations. And it also allowed each one of those pieces to evolve differently. So there was more. But when more changed and became less, less had more options available to it. If every application embedded the ability to do the equivalent of a paging function on a screen, every single application would have to change when you added this functionality. By allowing the paging of the functionality to be separate from the application, as a very simple example, this allowed you to scale applications completely differently from the paging of how those applications displayed their output on a screen. Microservices is an attempt to do that. But when you have so many different pieces, and you think about server VMs, or you think about server virtualization, each VM runs a complete copy of its own operating system. It's a completely isolated environment which gives you its own copy of the operating system. It boots up, it thinks it has its own keyboard, its own desktop, all of those different things, which makes it extremely heavyweight. In the enterprise, as an example, you typically have about 20 VMs running on a server, not more than that. And in many cases, it's far less than that. And of course, it also depends on what the application is. But when you start looking at things like running a LESS, running a simple Nginx, which is a load balancer, people started asking, why do I need the heavyweightness of a VM? Can I not just provide an isolated environment, and that environment gives me what I need? It's a much more lightweight virtualization. And out of that came containers, and out of the containers came microservices. We talked about the advantages of microservices, the fact that they are reliable, they make things more reliable because each individual component is testable, because it's far more simpler. You can release them much more quickly because if there are bugs, you can fix them and release them, as opposed to having a big, large monolithic application that just gets more complex over time. And like we talked about, it also reduces the barrier to entry for new frameworks and technologies, because it allows you to think about applications by breaking them out into individual components and thinking of each individual component as a piece that works and interacts through well-known interfaces. One of the things as a network admin or a network operator or a network engineer that becomes apparent to you is now application design has become much more a distributed systems design. Networking is at the heart of all of these things. People think about distributed systems design all the time. Networking people have been thinking about distributed system design for a long time, so this should lend itself to, oh, this is how you want to build networks, this is how you want to build distributed systems much more easily. Another interesting observation is the fact that networking and computing have been evolving at different speeds and at different directions. Given the advent of Linux networking and open networking, where Linux is the model and everything that you do looks like a driver, which essentially hardware accelerates the packet forwarding the Linux kernel, you can now begin to see if it's possible for us to evolve networking and computing at the same speed. As an example of this difference, microservices tells you that the application people are thinking that breaking up an application into smaller individual components and managing them through orchestration is far more interesting for an application developer. On the networking side, there are still people, it's 2016 I know, but there are still people who think OpenFlow and a central controller is the right model. So when people think about distributing applications, we have the networking people thinking we want to centralize applications. So there is this dichotomy that's continuously coming up that I believe consilience of networking and computing will address. But that's a topic for another day. Microservices, if you want to know more about it besides more than the introduction that I just provided, I think this Nginx blog, which is an introduction to microservices, has an excellent 7-part article. It doesn't really cover networking, but it's a very nice article about the architecture itself and why people are interested in it. So I think if you want to read it, I recommend it. So the Linux containers, if microservices are the genotype, then containers are the phenotype, for those of you who know your biology. Containers is essentially a Linux construct, which is a system isolation method that's lighter than a VM, but that's heavier than solutions such as chroot or systemd and spawn. So for those of you who know your Linux or your Unix, you know what chroot does. But Linux containers does more than that. It first of all doesn't assume that the entire OS is isolated. So for example, if you containerize your application is typically running on a Linux box. If you cannot have an application run somewhere else. The next thing is an underlying OS is common across all containers. When you run a VM, for example, one of the things I had to do to make this presentation is run a Windows VM on my Linux machine. A container assumes that everything that's running is in the host operating system, which is essentially Linux. So there is a question which is, why is a container lighter than VM? Because it does not assume that the entire operating system is there. It does not assume that the hardware is virtual. It does not assume that your keyboard is virtual, that every VM has its own notion of a keyboard. Essentially, containers assume that the host has all of the things that's required. It just essentially carves out isolated resources, slices the resources that are available into isolated chunks so they can use the resources without stomping on each other, but not really assume that everything is virtual and an abstraction that's provided to them. That makes the containers actually much lighter. And you will see an example of what I mean by that. The container landscape essentially is, if you look at the architecture, there is the Linux kernel that provides two fundamental constructs called C groups and namespaces. Those two fundamental constructs are what Docker, OpenBZ, Rocket, which comes out of CoreOS, all wrap around and provide nice, how shall we say, simplified mechanisms to be able to create containers. Applications run on top of one of these frameworks, which is a Docker or an OpenBZ or a Rocket. And Docker today has the mind share, most of the mind share. So whenever people talk about containers, they almost think it's Docker all the time. But there are other things going on in that space. We won't have time to get into all of that. But essentially, applications run on top of these frameworks. But this is the fundamental model. The Linux kernel provides C groups and namespaces. You have got constructs like Docker, OpenBZ, and Rocket, which provide you the ability to simplify how you use these constructs in your applications. It's almost like the Linux kernel provides you the x86 instructions. The Docker or Rocket or OpenBZ provide you the compilers, and the applications are written with the compiler in mind, not the basic instruction, because you're not writing assemblers. So with that said, let's get on to talking about container communication, which is the heart of this presentation. If containers are the phenotype for microservices, networking and communications is at the heart of it. So let's start looking at how containers talk to each other. I have a question. Can I run multiple containers at the same time? Absolutely. The question is, can I run the multiple containers on multiple hosts and have them communicate? Absolutely. We'll go over all of those as we move forward. So the topology, everything that I show here is done using Vagrant. The switches that you see here, spine 1, spine 2, leaf 1, and leaf 2's label is missing. Leaf 1 and leaf 2 are all running Cumulus VX. We have a new release coming out in the next day or two called 3.0, and it's all of this running Cumulus VX 3.0. 2.5.6, the last stable version we had, works as well, but this is fine. The hosts are running a box called it's a trusty Ubuntu trusty box, but that's been pre-installed with Docker. That's the name of the box that's been provided. I'm essentially running a layer 3 network between the leaf and the spine. The hosts in each rack are singly attached, and essentially the subnet stays within that rack. We'll cover more complex topologies, more complex situations separately, and we have covered that in the past as well, so I don't want to take the time to talk about it. But this is the topology that we are going to be using when we talk about the rest of this. So Docker essentially has two main networking options. I say Docker, again, as a synonym for container, just the way photocopiers, Xerox was a synonym for photocopiers for a long time. Docker is a synonym for containers today, but Rocket supports exactly the same modes. Essentially, there's a single host mode and there's a multi-host mode. When I run multiple containers on the same host, the containers need to be able to talk to each other. And these are the modes that are supported in that particular model. When I have multi-host, where I have containers across multiple hosts running in different hosts that want to communicate with each other, these are the models that are available. Essentially an overlay, a MacVlan, an IPVlan, and bridged. So the bridge that you see in the single host mode, which is the default mode that a Docker spins up, a Rocket spins up with, multi-host, bridged, is an interesting thing. This is the way a networking dude looks at how container networking works. So we'll talk about all of that as we get along. So there's a question, is it possible for a Docker container to communicate with a Vagrant machine? And I presume what you're really saying is, if I have Docker running inside Vagrant, can that communicate with other boxes running outside? Yes, and we'll see that in just a second. So let's look at what the bridge mode looks like. The bridge mode essentially, which is the default mode, there's a Docker 0 bridge that has been defined, it comes with a default subnet. The default subnet is randomly picked, but it comes out of the 172 space. So essentially it picks up the 172.17.00/16. It picks up a /16 subnet space to associate IP addresses to the containers. As each container spins up, you have the ability to specify what the IP address of the container needs to be, or just let Docker decide what the container IP address is, and it just sequentially picks up the IP addresses. Just following standard networking constructs, the Docker gateway is assigned 170 the .1 address, and everybody else is assigned subsequent addresses from there. When you start up, the basic default mechanism is you essentially have Docker containers that are able to talk to each other. And we'll see each of these in just a second. So when you look at what is the default communication mode that Docker allows, this is the default communication mode that Docker allows. Essentially what you have is you have these various containers that can communicate with each other, that these various Dockers can communicate with actually an upstream node, but they cannot communicate with another Docker bridge that has been constructed in this network. And we'll see all of these in just one second when I switch to the demo. So give me a second while I switch to the demo. So if you do Docker PS, essentially you see that there's a single one that's running, but the way you start, let's also look at the links that are on this box. As I said, there is a Docker 0 here that essentially is the default bridge that's been created. And if you type the IP, look at the IP address of Docker 0, you see that it's essentially gotten a /16 subnet that is working, that essentially has been assigned to it. There is ETH1, which is the uplink interface to the top of rack that is there. ETH0 is the management interface that's created by Vagrant. And these VETHs are the devices that are constructed or built up dynamically as containers spin up and spin down. So you see in this particular case that you see there is a VETH2 with this particular name. Well, let's spin up a container and we'll see what happens over here. Let's spin up a container. We'll call it sh1, and we'll say that what I want you to do is download an image and run. So this is an example we are already in. This is an example of how quick it is to spin up a container. It's no different than as if you're spinning up a process on a Linux server. Compare this to if I had to do this on a VM. It's much more complex, takes much more time. The infrastructure required is a lot more sophisticated, whereas here it just spun up. If you look at the IP address on this box, essentially you see that the IP address has been assigned 172.0.3. The reason why this has been assigned that address is because there is already one container that's running. Every container gets a subsequent address. The first container, which is this one, has gotten the address of 02, and so the shell that we spun up has got an address of 03. And now, as I did earlier, if you look at the links, you see that a new VETH device has been created. This is the device that's created as part of the container spin up. And now if I can go back to the Docker, and if I look at the IP address in here, I see this. I can ping 172.17.0.2 and I'll get a response back. So I can essentially communicate with another container that's connected to the same Docker bridge. Let's start another one. I can connect to the default gateway as well. Now let's just say I want to type update on this. And you can see that it will essentially connect to the upstream node, and this is going out to the internet and coming back. So you can see that this container can also communicate with the outside world. So the basic communication mechanisms that we talked about all work. Now let's create another. If you look at what are the networks that exist, and you can do that with a ls, you'll see that essentially there is a basic default Docker. Let's go ahead and create another network, which is a bridge. And let's assign it IP subnet, which is equivalent to a different one. Let's call it 172.18.0, or let's just take 22.0/0/24. And type is bridge, and I have to give it a name actually. So let's call it Docker1. Sorry. So it did not create. So clearly I have mistyping. Create. I have typed this before, so I'll just go look for what I had typed earlier to get me to do what I want. There it is. So there is network create minus subnet Docker2. There it is. There was no equal to involved. So I have now created a subnet, a new Docker bridge, and you can see that if I type IP link, that there's a new thing called Docker1. But internally it's called Docker1. Externally it is called this particular IP, this particular name. And you see that it's been assigned an IP address 172.16.2.430. So this means that I can create just one more container in this because 30 is already taken up. 30 essentially means you can create 2 hosts. So let me go ahead and run a new Docker image. I'll say the name is sh2. I'll say the network I want it to connect to is Docker2. Was it called Docker2? Yes, Docker2. And I'll say that I want it to essentially run the same Alpine with the shell. And it's in. Now let's take a look at the IP address here. The IP address here is 172.626.30. We know that we have got a 172.17. Let's see if we can go ahead and ping the 172.17. We know that there was a .2 and a .3, and you'll see that it will not communicate. Same thing with 3, it will not communicate. Okay. Who can I communicate with? Can I communicate with 5? No. So who is really allowed? Who can I really talk to? So there is a 6. So there must be 2.5, 16. That's the default gateway, and I can communicate with that. Can I do the update like I did before to the external world? Yes, I can communicate with the external world. So to come back to the model that we talked about in here, essentially, I'm switching back to the slide. Give me a second. You can see that we allow communication within each Docker bridge, but across the Docker bridge, communication is not allowed. So the way this all works is essentially NAT is used for external communication. Let's take a look at what we mean by NAT is allowed for an external communication. The basic idea is that you're using IP tables and you're using NAT as a mechanism to communicate with the external world. So if I attempt to ping anything from inside to the external world, then it will use a separate IP address, and we'll see what that goes on in 1 second. So there is a question. There are a few questions here. Let me try and address them quickly. Is this using DHCP? This is not using DHCP. Docker is essentially sequentially assigning IP addresses one after the other. Can we type commands like iproute get and inside the container? I believe so. We can take a look and see what it types. So let's type iproute get 10.1.20.1, and you can see that it essentially is going through the default gateway. But let's go back. So we are connected, host 11 is connected to leaf 1, which is assigned an IP address of 20.1. This is the bridge to which the hosts are all connected. So let's take a look at what's going on if I say bridge.20, show me all the ICMP packets please. I want to see what's going on. So now let's go back over into the container and just ping 10.1.20.1 and see what happens. You'll see here that what's coming out is really the NATed IP address of 10.1.20.11, which is the IP address of this interface's connection to ETH1. And you'll see that if I just type IP address, you'll see ETH1 has 20.1.20.14/24, and that's the IP address that's being used. So essentially, any external communication from the container is all happening through NAT. That's the fundamental mechanism. So the basic idea is if I start deploying containers in the cloud providers do not allow you to expose the internal IP addresses. So via the NAT, you NAT to a public IP address, and everything is done using NAT. To come back to the presentation, we just went through what a single host networking looks like. And there is a question, but how do I really want to do multi-host networking? This is great. I can do things within a single host. I want to reach across hosts. How do I do that? This was essentially a command function that was introduced in Docker version 1.10, I believe, and it uses VXLAN overlays to essentially connect L2 networks. So I can have a bridge running on host 1, a bridge running on host 2. Both of them have the same subnet, and essentially VXLAN overlays are used to stitch these two subnets together. I will not do a demo of that because to build a multi-host networking is actually pretty complex. You have to first build a virtual machine, or you need a separate machine which is going to be the key value store. Then you need to have all the machines to be able to communicate with this key value store. Then you need Docker Swarm, which is a new piece of software that Docker introduced in order for you to have multi-host networking work. So essentially the number of pieces that you have to have working to get multi-host networking work is fairly large. And you go, oh my God, that's quite a bit. So I decided not to do that and instead take a contrarian view. I decided I'm a networking dude. I know how networking works. What the heck are these guys doing inside the containers? Can I try and understand that so I can break up everything? Before I proceed, there are a couple of questions. Is there always one vETH running for each running container? vETH, essentially they create, this is now getting into the details, they create two vETHs and they tie the two vETHs together, essentially like a pipe. One vETH is put inside the master, inside the Docker. Another vETH is put inside the network namespace, inside the container. So the container thinks it has got an interface called ETH0. It's really just a pipe to the master bridge, and to another vETH that's sitting in the master namespace. So essentially, there's always two vETH devices created for every single container that you spin up. So the question is, how does a router function work across containers and VLANs? The router function works across containers and VLANs depending on what driver you're using. In this particular example, we are using a bridge, and when you're looking at a bridge, essentially the model is packets going out get routed. Packets, the Docker bridge acts as the default router. The Linux kernel provides the routing functionality, and it looks up the routing table in the master, which is essentially the Linux host, and forwards packets to and from. And as you saw, there is a natting function that's going on that's also being done by the Linux kernel to make things work. There are other modes that we'll cover later that do things slightly differently. So the question of how does a router function is going to depend pretty much on the driver you're using. In the case of the bridge, it functions a particular way. Having said that, let's get on to looking at what is multi-host routing. Can I look at multi-host routing or multi-host networking in a far more simpler fashion? So why do we do these NATs? We talked about it, why we do NATs. But these reasons are not commonly the case for people who are trying to deploy containers in their own data center. Unless they are cloud bursting, meaning they've got half their Docker containers running inside their private data center, other half running in the public cloud, and the two need to communicate, etc., etc. The most common use case that we have encountered internally is because of the microservices architecture, people in the data center are building all applications this way, or moving to building these applications this way. All is a pretty strong word. But when they are doing that, they don't particularly care about trying to use NAT because the IP addresses they are using inside the data center are just IP addresses inside the data center. So what can we do for such folks? Is there something that we can do for such folks? Yes, we can. What we can do is turn off NAT. You don't have to enable NAT. You can assign non-default IP addresses to the Docker bridges. You just saw an example where I created Docker 2 and gave it a different IP address. And essentially, you can run a routing protocol on the host to announce these addresses. And we'll just do a quick demo of that. You can also, from the purposes of when I was explaining all of this to some other people, they asked me, can I not just build a giant L2 network with each host doing IPAM over, or that is IP address management, over a smaller set of that subnet, so that I'll have host 1 with bridge and host 2 with a bridge. And essentially both of them are having a subnet which is common across them, but both of them are allocating IP addresses which are a subset, so they don't stomp over each other as containers are spun up. And can I make a giant L2 that connects all of this together? Yes, you can. But go ahead, build a giant L2, and we have had various discussions about what such a construct involves. It's far more easier to build, or far more robust, scalable, and flexible to build a routing protocol to do this. And we'll show that in just 1 second. So first things first, what you need to do is go on and stop all your Docker and restart Docker with a different set of options. So you stop Docker, so it turns off all the hosts, turns off everything, and it just give it a minute as it shuts down all of the different containers, and it'll stop. So now if you do ps-ef, if you look for Docker, you see that there is no Docker running here. So now let's go and enable a particular option inside Docker, which is these two key pieces here. The first piece is, hey, don't do any fancy IP tables for me, I'll take care of it. Hey, don't do any masquerading for me, I'll deal with it. So I know what I'm doing, please turn those two things off. Having turned those two things off, let's restart Docker and see what exactly happens again. So Docker is started. If I do, so I have to go back and take a look. Can you see the screen now? What I did here, for those of you who wanted to see, is essentially I went into Docker default Docker, and I added these two options, which is essentially turn off IP tables, turn off masquerading, and I'll deal with everything myself because I know what I'm doing. And then I started Docker, and essentially, as usual, the Docker that runs on this particular host has a default that it starts up to gather some metrics. It's called CAdvisor, which is a monitoring framework that done by Google, and it monitors containers. So they just have it running by default. So you started that. And now if you look at what the IP addresses are, nothing has changed. I have not changed any of that. So essentially you have Docker 0 with IP address of 172.17.1. So let's go back and create another container and say minus name is, minus name is sh1. Let's give it, let's start alpine /bin sh. Oh, what the heck happened? Oh, it's already there. Okay. Let's give it a different name. That's also there. Let's call it something else. /1. Okay. So you can see that the IP address it got is 172.17.03. None of this so far is very different. There is one thing I have to do. While Docker stop takes care of certain things, it does not clear the old IP tables. And you can see that if I type IP tables save, all of this is still present. So let's go ahead and stop Docker again. Clear up all the IP tables and start the service again with the options turned off. So sudo IP tables -flush -t nat. Turn off flush all the rules for nat and for filter. And if I do IP tables list, show me what's there, you see that there is nothing there. Perfect. Now let me start Docker as a service again. If I do Docker ps, I see that again. If I do Docker run minus name equals -2, because I created one, I don't know why it is I guess I'm still learning Docker. So alpine/bin/sh, I'm in. I look at the IP address, I'm back to 172. So remember, when we attempted to ping the router, the IP address was getting natted. Let's try the same thing again. Let's ping 10.1.20.1 again. And now you see that the IP address that's showing up is the unnatted IP address. So essentially now the IP addresses are not getting natted. Okay, this is very nice, you say. What exactly have you achieved, Dinesh? So let's go create another bash, and we'll see what happens in this particular situation. And if I look at the IP address here, you see that it's 1.4. If I ping the information, you see that the outside world is seeing the specific IP address. And can I ping my partner who is running in the .3? Of course I can. Can I ping the .1, which is the default gateway? Of course I can. Can I update the software? Can I reach the external world? And you see all of these things work exactly the same way. Now let's take a look at a slightly different thing. Let's go ahead and create another container, but this time connected to a different Docker bridge, and see what happens. So docker run --name equals bash 5 --net equals docker2. No, that was already there. So docker ps. So I just have to go back and docker start. I think it was called sh2. Yeah. So can I connect to docker attach sh2? Yes. And what's running here? You notice that this subnet is a different subnet, right? And in the past, when we attempted to talk to 172.17, which is a container running in a different Docker bridge, we could not. Let's see if I can actually ping. I see that the ping works fine, but packets are not coming back. Okay, that is not very good. What about, can I actually ping a partner namespace? Yes, I can ping a partner namespace. Can I ping, the partner is 0.3. And you can see that I can actually ping that. Whereas before I could not have a Docker container connected to two different Docker bridges talk to each other, now I can actually make that work. Let's go ahead and fix a few things now. I will get out of here and essentially start Quagga, which is the open source routing protocol on the host. With this done, now if I go back in here and I ping the external world, the world is working beautifully. This is because the IP addresses are now being announced from inside the on the host. All the container Docker IP addresses are being announced, and so now I have connectivity. This is great. So I have connectivity to the external world. I have connectivity between, but don't I want to have some microsegmentation? Yes, you can. And the way you do microsegmentation is you add the IP tables rule that you want, which is essentially saying, look, from anything from 17, which is in Docker Bridge 1, I don't want you to talk to anything on Docker Bridge 2. Drop this packet. That's what this IP tables rule is saying. So let's add that. Let's go back to this one and attempt a ping to my partner, which succeeded before. And it's still succeeding. This is what happens when I do demos. So let me go back and actually take a look at IP tables -L. It's there, but drop 172.16. That was the IP address, and it's saying, okay, so let's also add to the output. Oh, yes. The reason why you saw the rule actually not work. Before we do anything else, let's first go back. That's the only thing. it says from the source of 17, anything going to this. So instead of trying to do it the other way, let's do it the right way, which is we say docker attach -1. Oh, docker ps docker attach. Let's just connect to this one. No, that's the first one. So let's connect to this one. And if I do IPA, you see that it is in the 172.6 subnet. No, that's not the one I want. I want the other one, the one that's connected to the other subnet. Yes. Now, if I attempt to ping 172.16.2.6, it's working. So I have to go back and add that additional rule. Sorry. So here is the IP tables rule. 172. Yeah. So let's go ahead and add the IP tables rule, which also says.
Somebody say.
I will just do that, and now go back to my little docker attach and ping, and bingo, it doesn't work. So essentially, the point that is important. Thank you for the sharp eyes. I appreciate it. Where is this thing? I got to stop sharing the desktop. That's the reason why I have to do that every time. So to come back here, when I do this, essentially the mechanism is that by doing simple Linux bridging coupled with routing on the host, I get multi-host container communication without requiring me to do complex stuff. I know that I just showed you everything on one host, and we can do it, but in the interest of time, I want to run through. But it's possible to look at all of this in a separate way, and you can do this yourself and actually see things work. Yes. So there is a question here, which is there are two questions. What terminal emulator are you running in there? I run Linux as my primary desktop. I use something called Biobu, which uses tmux. So it's a tmux front end. And I see a lot of network stuff happening with Docker containers. How does this relate to Cumulus Linux? You mean you're not just interested that there's something interesting being shown? Well, how does it relate to Cumulus Linux? Part of this particular series, and I just want to kind of highlight this, is this is an attempt to demystify networking, to tear apart pieces and put them together so you can actually see how things work. Some of it may have no connection to Cumulus Linux at all. This is an attempt to educate people on networking and be able to think. On a specific with my marketing hat on, which is a very small hat actually that I wear sometimes, the key part is that when you have open source routing that runs on the host, you have the ability to do multi-host networking. The open source routing suite that is out there that's prominent today is the one that we put out called Quagga, and it's a upstream, it's a modified version of Quagga. Patches are upstream. So all those questions about are we upstreaming the patches? Yes, we are. But essentially it's an open source routing suite called Quagga, and using that we enable multi-host communication to happen in far more simple ways. If you can do basic bridging, you can type IP tables to configure all your communication, then you got the behavior that you want, which is essentially microsegmentation, and you've got multi-host communication using ideas and technologies that you already know and understand. So that's how it relates to Cumulus Linux. But also another perspective, Cumulus Linux is about Linux networking. We want to show that Linux networking is at the forefront of how people are thinking about networking, and we are working with the Linux kernel community, with the open source community to make sure that Linux networking is a first-class citizen. So to educate people about anything that is Linux networking is part of Cumulus Linux's mission as well. So there are 3 or 4 different ways. So we talked about bridging. In the interest of time, I want to kind of go very quickly over. We have a lot of choices here. Do we need more choices? Why do we have more choices? I mean, you say that there are even more choices. Yes, the primary problem is bridging the default way when you enable Docker involves NAT. When I think about 1,000 containers and 1,000 NAT rules, just think about the performance that you're going to get because of that. Because NAT is not scalable and it has performance issues and also complicates troubleshooting. Also, it is not able, you cannot assign IP addresses to containers without regard to the bridge subnet. Why do we care? There are certain use cases where people care. There are two separate models that are out there. One is called the MacVlan model, which essentially is an older Linux kernel driver. So MacVlan is not anything, it doesn't necessarily use VLANs. It essentially constructs multiple MAC addresses on a single physical interface, and the driver looks at the packet coming in to decide which virtual NIC, in this particular case container, to give the packet to. In the interest of time, I'll move on. The next one is IPVlan, and in IPVlan, which is yet another driver inside the Linux kernel, IPVlan does not have anything to do with overlays, does not create a new way of constructing IP and IP encapsulation, none of that. It's just a driver. The basic idea is an IP interface, a VLAN interface is created, and inside that interface, you can associate any number of virtual interfaces. Each of those virtual interfaces can have their own IP addresses without regard to any subnet. When IPVlan is run in L3 mode, those different containers running different subnets can communicate with each other. There is no IPAM, that means there is no DHCP, because there is a single MAC address being used across all of these different slave interfaces. You cannot use DHCP to assign separate IP addresses to each of them. So you have to manually configure IP addresses when you launch the Docker instance, as you can see in this particular example. Also, all broadcast and multicast are dropped, so no ARP works, none of that works. What it lets you do is build a very nice, isolated, well-controlled container network for yourself. But on the other hand, it does not use many of the Linux kernel constructs. All the routes that are created as part of the IPVlan are hidden inside the IPVlan driver. They are not visible via IP route show. They are not visible via netlink. So it's not exactly a great model, and our next webinar will cover some of the alternate solutions that are being looked at by various people for that. I promised to talk about a few other things, and in the interest of time, I'll quickly move on to those things. So if you've got all of this covered and we know how multi-host networking works, why do we need container frameworks? Do we need anything else? What is Kubernetes? What is Mesos? What is Calico? Do we need all of those? Multi-host containers require more than just communication simplification, right? There is cluster management. There is job scheduling. There may be policy. There is service discovery. There is lifecycle management. All of those are provided by these application frameworks. Swarm is the one that Docker provides. Kubernetes is something that we did last time. Mesos, Weave, all of them are different application frameworks that allow you to do all the multi-host container networking, the problems, the parts that are not handled by just doing simple routing plus bridging. There's also Project Calico, which does more than that. It also attempts to simplify policy and allow you to do policy. And you see little green boxes everywhere because they have things called network plugins. They plug into Swarm. They work with Swarm. They work with Kubernetes. They work with vanilla Docker. They work with Rocket. All of those different pieces they plug in and they do things inside that. So we are coming to the end of our presentation as we are coming up to the end of the hour as well. What I did not cover network plugins. I did not cover host mode. I did not cover Flannel. Flannel is very similar to the overlay driver that exists inside Docker. Flannel came out of Rocket Core OS, so that's a different, but they pretty much function the same way. The common use case I've seen with Flannel is with Kubernetes, but as we talked about it, even Kubernetes does not need that. If you just run vanilla bridging, routing on the host, you can do all kinds of interesting things without requiring any fancy, complicated new overlays or technologies. So in summary, microservices are the next evolution in building scalable, resilient, and agile applications. Container networking has many new and moving parts, but at the heart, just the basic Linux bridging and IP tables are good enough to provide communication and segmentation. And running a routing protocol on the host just simplifies multi-host container networking phenomenally. You don't need new drivers. You don't need anything fancy. Just basic stuff works pretty well. With that, we come to the end of this webinar. The next month's webinar is going to talk about operationalizing Linux WRF in the data center. The guest is going to be David Ahern, the primary WRF author inside the Linux kernel. And we will see how IPVlans evolved to VRFs and how VRF solves the problem in a much nicer way using all the constructs and the Linux structures that we understand. With that, I thank you. I hope you've had fun, and I hope you learned something. Thank you again for taking the time. I look forward to seeing you again in the next episode of this webinar series. Have a wonderful day. Bye-bye.